Hi everyone and welcome to the presentation. We'll be discussing a survey of planning systems used in commercial video games published by Neufeld and colleagues in 2017. I'll be talking about algorithms like strips and HDN and certain environment analysis ideas. My friends will cover domain creation, agents and goals, actions and plan execution. So just to unpack the idea a little bit and put things into perspective, here's an example from a typical GTA 5 situation where you as the player can basically explore the world, walk around, talk to people, drive a car, use a cell phone, things like that. And an NPC or a non-playable character is an artificial person that coexists with you in the simulation. These could be things like people, vehicles, animals, basically anything, a robot, an alien, a zombie. The NPCs can display very human-like behavior, like responding to your actions. They can talk to each other and even coordinate their movements to achieve an advantage over you. The NPCs usually follow a script, a predefined script, and may have specific routines and actions and things that are triggered by the human player when you interact with them. So looking at the huge number of video games available on the market, you would think that there's a massive variety of algorithms and stuff being used, or that people develop their own ones. But actually this is not the case, and according to the authors of this paper, in most cases it's strips or some modification of it that's being used. So most games use planning systems as opposed to, say, classical planning or search, because a planner allows us to look ahead in time instead of being purely reactive. But this can be difficult to implement in dynamic environments, as we'll see. Methods of AI, as we are used to in academia, have limited application to commercial games and are hardly ever used. Classical planning, as opposed to modern state-based planning, makes certain assumptions about the world. Classical planning assumes that the world has a finite set of states and is fully observable and static. A solution or plan is assumed to be an ordered set of actions and actions that lead to instantaneous transitions between states. I know it can seem a bit simplistic to say that classical planning makes these assumptions and therefore we don't use it. I mean, we know that there are many different variations of classical planning that could be adapted to video games, but basically, commercial game designers don't care so much about that and they use whatever works best. So, in this case, strips is a very famous and well known algorithm developed at Stanford in 1971 by Fikes and Nilsson. This was used in the shaky robot. The main purpose of the algorithm was the creation of plans for the robot to rearrange objects in a room. So the robot would search, or the algorithm would search through a set of states, the world space, to find a state in which certain conditions are true. And if the condition is true, it would apply a certain action, as we'll see. The world state is represented in first order logic as well formed formulas. These are referred to as facts and they describe properties of the world using functions. So here's an example of a very basic strips algorithm. It has an operator on the left, or a function taking two arguments. The arguments can take on values, for example, agent 1 and home, that tells us agent 1 is at the position home. The operator is a symbolic representation of an action and is defined by its preconditions and effects. So let's unpack the algorithm a bit and have a look at the elements that control the flow of the program. At the top here we can see the operator using a go-to action that tells the agent to go from a start position to a destination position. In order for the operator to work, it has a precondition that must be met. So in order to go from point A to point B, you need to be at point A first. When the action is applied and you go from point A to B, then this effect has to be somehow recorded and remembered by the algorithm. So in the delete list, we would have the state that has been performed and is no longer true, and this is simply forgotten by the algorithm, and the new state is added to the add list as new knowledge, and the destination now becomes the start position and can be used again by the algorithm. So just to make a very simple example of how this can actually be used in a game to perform an action, let's have a look at the GTA example that we saw from before. I don't know if you can see in the top left corner here is a little dialog box that says police partner standing by, stand face to dismiss. So in this case, the algorithm would handle the action of turning towards the partner and causing an effect such as the partner being dismissed. The operator tells my character to turn towards my partner, going from his current position to a new position, and when the action is completed, the old position is deleted from the list and the sequence repeats. Systems like this strips algorithm are known as state-based planners, and they use theorem proving to search for operators that resolve away clauses. As you might remember from Introduction to AI, the horn clauses and the theorem resolution. Operators that reduce the difference are added to the list. So in most cases, commercial video games use strips or some modification of it, and some milestones in game development include the release of Fear in 2005 and Killzone in 2009. Fear used a system called the Goal-Oriented Action Planner, and Killzone implemented something like a hierarchical task network or HTN. In the interest of time, I'll only touch on this briefly, but the point I'd like to make is that these are still very similar to the original strip system that we're used to. Um, I suppose the difference would be that if you have really complex operators, the search tree would grow quite rapidly, and you could implement heuristics to minimize the number of states that are searched when operators are selected. Another minor difference would be the way that data is represented by the algorithm. So the effects and preconditions would be represented as arrays instead of logical statements. In conclusion of my section, I'd like to touch on a few aspects of environment analysis and how it affects the game situation. As you might expect, the world state in the game needs to be a stable construct that appears the same way to players and non-playable characters or NPCs. For example, if you are in a certain place in the game and you leave and go back to that place again, then it needs to look the same as before. But players and NPCs are in different locations and have different knowledge about the world. This means that we have to make the world partially observable to different agents trying to use it. So it's possible for a game agent to have full observability of the game environment, but games actually limit this to create a more human-like experience. So if the player cannot see through walls, then neither can the agents. Take an example from Metal Gear 5, where you have to sneak around the camp and avoid detection. This would mean that you cannot be seen by NPCs, and NPCs may be hidden from you. So the player and the NPCs are actually accessing different information from the environment. Games often use verbal communication between agents, which you can actually hear, and the conversations, though scripted, can appear quite realistic to the extent that it seems the NPCs are following each other's voice commands. But whether or not the world's observable, some data has to be saved for the planet to have a symbolic representation of the world, right? So this is achieved by using a kind of blackboard that can be accessed by one or more agents so that some NPCs can have different knowledge from others. So in summary, commercial video games use planners instead of behavior trees, finite state machines, or classical planning. Strips was successfully used in Fear and spawned subsequent adaptations. These algorithms are based on simple predicate logic and theorem proving and are composed of operators, preconditions, and effects. Thanks everyone, and I'll hand over to my colleagues for the next section.
Okay, so I'm gonna pick up where my friend Waldo left off, and I'm gonna start talking about domain creation. So, domain creation. What is a planning domain? A planning domain is like a library that contains knowledge about the game world. It includes planner components, which are the building blocks for making decisions, and these include operators, facts about the world, and methods for hierarchical task network planners. When creating a planning domain, developers need to focus on making it readable and extensible. And this brings us to the first aspect of domain creation, which is domain compilation. The planning domain translates important game information into a format that the AI planner can use. This involves turning game actions, their preconditions, and their effects into data structures and code functions. There are two main ways to do this. First, direct coding in the planner's language. This method involves defining the domain directly in the programming language used by the planner. For example, for the game Transformers Fall of Cybertron, programmers define the domain in the game's code. This method is straightforward for programmers but can be inflexible and slow to modify. The second way to do this is to use an intermediary language, for example, like a high level language like Lisp, to define the domain, which is then compiled into the planner's code. This method was used in projects like SquadSmart, and it will allow for more flexibility and easier modifications, but overall is a bit more complex to set up. Now we move to learning versus specifying domains. So traditionally, developers manually specify the planning domain for a game's AI. This involves defining precisely the actions, conditions, and effects that AI uses to make decisions. But an emerging approach is to have the AI learn the planning domain instead of being manually specified by developers. This means the AI would develop its own understanding of how to act in the game world. So, while learning the domain is a popular research topic in academia, it's mostly tested in simple and deterministic, that means predictable, environments. On the other hand, commercial video games have way more complex environments. And I mean, anybody who is a gamer here can attest to that. Commercial video games need huge teams to work together in order to make an enjoyable experience. So, learning a domain for this could be a challenging but interesting task for both developers and researchers. So, a few of the challenges and disadvantages of learning the domain. A learning domain may not always produce the desired behaviors, and it might be harder for developers to understand, debug, or modify. Learning a domain can take a long time, which is a significant factor in game development, where developers have limited times and deadlines. For offline games, this process might be too time consuming, but it holds great potential for online games. Online games could use player data to continuously adapt and improve the AI. There was an application of this in the Tomb Raider game. The game's AI domain was manually defined, but the costs of actions used by the AI to make decisions were learned and adapted during gameplay. Learning the domain is an innovative approach where the AI develops its own understanding of how to act in the game world instead of relying on predefined rules. This method offers potential for creating more dynamic and adaptable AI, but comes with challenges like complexity, time consumption, and unpredictability in behavior. So, to recap, to summarize, domain creation in AI planning for games is about building a knowledge base, the planning domain, that the AI can use to make decisions. This involves coding game actions, conditions, and effects in a way that the AI planner can understand. Developers must balance between making this domain easy to read and modify, and the technical challenges of setting up a system that can handle complex game behaviors. And now we move on to goal creation. So, goal creation. First, we need to define the goals. In AI planning, goals are the objectives or end states that the AI is trying to achieve. The process involves determining what the goals should be and how they will be selected and managed. No matter what kind of a planner is being used in the end, plans are always created to achieve some goals or bring the game world into a certain state, goal state. So, there are a few ways to satisfy a goal or to decide when a goal is actually met. Goals can be simple and categorical, like, for example, move from point A to point B, or they might be only satisfied to a certain degree, like, for example, collecting a sufficient amount of health potions. Developers can set thresholds to decide when a goal is sufficiently satisfied. These thresholds can be fixed or fuzzy for variability in AI behavior. And this brings us to goal duration. Some goals might be only temporary. For example, they are achieved when a certain condition is met, while others are durative or permanent. Durative goals are ongoing and can only be replaced by other goals. Often, it is desired that the agent follows the player, stays in his view, or simply stays alive as long as possible. These goals cannot be declared as satisfied at any certain point in time. And some goals can be in competition with other goals, so to speak. AI agents might need to pursue multiple goals simultaneously, like moving to a point while staying in cover. This can be challenging, especially when goals compete with each other or can't be easily quantified. Some games use multiple planning domains to manage different sets of actions or goals. In real games, this could be like having one part of the game's programming focus on your movement, while the other part focus on the visibility of enemies. Uh, some way to implement this, for example, is to have one aspect of planning focus on the players in soccer games and their positions, while other aspect handles their stamina. Goal selection. So deciding which goals to pursue and in what order is crucial. This can be done through prioritization or more complex decision-making mechanisms. Goals might be assigned by the player, selected automatically by the AI based on the situation, or determined by a hierarchy of higher level agents, assigning goals to lower level agents. If game agents are supporting the player, it might be possible to allow the player to assign them certain tasks that could be passed to the planner in order to create appropriate behaviors. In many cases, however, agents do not get orders from human players. Instead, they should be able to select their goals autonomously, taking multiple facts into account. So, to summarize, goal creation for AI in video games involves defining what the goals are, how they are satisfied, their duration, and how many can be pursued at once. It also includes developing mechanisms for goal selection, which can be influenced by the game's design, player input, or the AI's autonomous decision making. The approach varies based on the game's complexity and the desired level of AI sophistication. And now we go to the next part, which is agents. AI can be designed for a single character or for multiple agents. Multi agent systems offer better tactics and coordination, but also introduce more complexity. The number of agents actively using the planner at the same time is crucial. Games like Transformers Fall of Cybertron had many agents, up to 17, using the planner concurrently. In contrast, games like Fear and Rise of Tomb Raider had fewer active agents at a time. This, of course, depends on what kind of game someone is playing. Action games, for sure, need more agents at the same time to keep the player engaged, while horror games have fewer agents active at a time to increase suspense. So agents can be homogeneous, that means very similar, or heterogeneous, different types with varying abilities. And planning for heterogeneous agents is more complex. Different approaches include creating separate domains for each agent type or incorporating the agent type as a precondition in a single domain. In most video games, the agents are heterogeneous. Coordination is important in multiple agent systems. Agents can have cooperative or competitive behaviors. In cooperative scenarios, like team based games, agents work together towards common goals. This can be achieved using planners that allow for joint actions. In competitive scenarios, like real time strategy games, agents compete against each other. which adds complexity to the planning due to the need to anticipate competitor actions. The size and structure of agent groups can change due to death or new spawns. Planners need to adapt to these changes. Dynamic reorganization of groups based on the situation is important. For example, combining two smaller groups into a larger one when they meet. The planner should be flexible enough to handle different group sizes and compositions. A few examples from games are Shadow of Mordor, where up to 400 agents could be seen, but only a limited number were planned for at any time to maintain performance. In the game Killzone 2, a dynamic squad manager was featured that reorganized squads based on objectives and agent locations. So, to summarize, when creating AI for video games, considerations about the agents include their number, types, how they coordinate, and how the AI adapts to changes in team size and composition. These factors influence the complexity and capabilities of the AI planning system, affecting how agents interact with each other and the game world. And moving on, we have actions. So, determinism of actions. In video games, actions can have multiple outcomes, sometimes due to randomness or external factors. Different methods exist to handle this non determinism. First, we have probability distributions, planning for the most probable outcome based on predefined probabilities. Then, case based reasoning, that means using past experiences to predict future outcomes. Bayesian networks, analyzing dependencies between variables to predict outcomes. And conditional planning, that means creating plans for all possible outcomes. Though this can be complex and is less common in commercial video games. Actions in games often have a clear endpoint, represented by animations, but some actions are durative or persistent, like patrolling, which continues until a new goal arises or the task is aborted. It's important to manage these persistent actions effectively in the planning process to avoid repetitive planning and to allow for replanning when necessary. Considering the time aspect in planning is also crucial, especially when agents have varying speeds or capabilities. One approach is to include time in constant computations for actions, using heuristics. This helps in assigning tasks appropriately among agents with different speeds. Some advanced methods, like combining hierarchical task network with simple temporal networks, exist, allowing for more nuanced temporal planning, but these are still in early research stages and not widely used in games. In video games, hierarchical task networks help the game decide what the characters should do by breaking down big tasks like defending a castle into smaller tasks like patrolling walls, standing guard, etc. This helps the game characters to act more intelligently and do things step by step. Simple temporal networks in video games help the game understand the timing of different events and actions. For example, in a game, a character might need to pick up a key before opening a treasure chest. STNs help the game keep track of these timings and sequences, making sure everything happens in the right order. So, to summarize, planning for AI actions in games involves handling the unpredictability of outcomes, managing the duration of actions, and incorporating the aspect of time. Developers use various strategies, from simple probability based approaches to more complex conditional and temporal planning, to ensure that AI agents can execute plans effectively and adapt to the dynamic nature of the game environment. And now my friend Fernando will continue with our presentation. Thank you very much.
Hello everyone, I'm Fernando, and I'll be delving into the more practical aspects of implementing a planner system in a video game setting. So, how do we actually go about creating the plans? The process can be divided in roughly the three aspects that you see in the screen. First, the building blocks. We'll start with the preconditions and the effects, the core of any planning system. Here, we'll build up all the insights that Wardlow shared to see how these elements are defined and evaluated. Second, We'll discuss the planner's topology, which is informed by Eduardo's discussion on agent dynamics. This involves how do we structure our building blocks into a planner that is suitable to facilitate the type of agent interactions that we seek. And thirdly, the dynamics. This addresses the methods and strategy that actually build the plans. This includes selecting suitable search directions and pruning strategies that align with the structure and building blocks that we have at play. Let's start with the building blocks, and specifically with the preconditions, akin to the reasoning language of the planner, if you will. This involves how will we define the preconditions that the system must evaluate to arrive at a feasible plan. And you have two main paths. You can follow up on the academic tradition and use complex preconditions in first order logic, where the richness of this logical system allows you to really capture complex dependencies within the game world. As such, games like Final Fantasy XV took advantage of this and used it to represent the complex interactions and behaviors it needed to coordinate its background NPCs. However, this complexity necessitates a theory improver or a similar library when it comes time to evaluating these predicates, which is very computationally demanding. So while it might work great for background coordination, it might pose a significant challenge for gameplay-centric real-time planning. In contrast, Fear offers an approach of using simpler data structures to represent preconditions in a way that facilitates direct, efficient comparison. Specifically, it used fixed size arrays for goal state variables, enabling a direct comparison between the initial and the goal state. This method greatly enhanced computational performance. There's a trade-off, however, in that there is a reduced capacity for more complex checks and thus for more intelligent behavior or coordination. Fear addressed this problem by uploading a specific precondition checks like grade casting or path evaluation to functions external to the planner. In sum, creating a balance between definitional complexity and evaluation efficiency is a significant challenge. Too complex definitions can make the system unwieldy, while easier ones can oversimplify the AI behavior. The key here is using the tools available to find that middle ground that enhances the gaming experience without overburdening the system. The other building block of planners are the effects, or how the actions taken will change the world state. And here the practical choice is to decide whether we allow the planning system to simulate the effects of its actions in the world state or not. If we do so, then the system can generate very complex, precise plans far into the future. And this approach is demonstrated, for example, in Transformers, Fall of Cybertron, where the simulation was effectively implemented in its HTM planner. The effects of the actions changed the world state, and these changes were integrated during the planning process. Yet, as we discussed, an inherent aspect of video games is the dynamic and often stochastic nature of the environment, which makes it very challenging to ensure that the world states during the actual execution of the plan will match the states that were predicted during its creation. External variables can interfere, rendering the plan effects obsolete, so that the longer the plan, the more expensive it is to compute, and yet the more likely it is to fail. As we will see in part 9, this really speaks to the importance of having a proper replanning mechanism to adapt to the evolving game environment. An alternative approach might follow up on the game Dying Light and just save itself the trouble and the cost by simply foregoing propagation entirely, essentially removing the planner's ability to reason into the future. We'll see how this can work if the replanning is done often enough or if not many actions meaningfully change the world state, like just performing an animation. In sum, the approach that we use and how much foresight we allow the planning depends on the trade-off between accomplishing complex goals and improving the efficiency of the planning algorithm. Once we establish our building blocks, we can now turn to structuring the planning domain, and specifically the planner's topology, which will prove pivotal in orchestrating agent coordination and interaction. Again, there are two main alternatives. Centralized planners usually involve the use of an HTN and are easier to deploy because one of the main advantages of this architecture is that coordination can be directly and efficiently defined within its planning domain. This also usually translates to more clarity and ease of debugging, as there is only a single source of knowledge and orders to the agents. Decentralized planning, on the other hand, allows individual agents to possess their own planners, facilitating a more organic and varied interaction. However, this poses the extra challenge of ensuring efficient communication among agents, particularly regarding plan failures, without overwhelming the game's performance. A few ways of ensuring this may include restricting communications to within a local radius only, or a hierarchical system where, for example, soldiers only inform commanders and only commanders can give orders to soldiers. Yet still, developers might seek a hybrid approach, use a centralized coordination system to handle the communication among these decentralized planners. This was the approach used by Fear, which deploys a squad coordinator on top of his co-planner because it was just much easier to implement and debug than having the agents try and cooperate locally. Still, regardless of the chosen topology, a critical aspect is balancing the information flow. For centralized system, it's about determining optimal times for agent to update the central memory and to read information from it. For decentralized systems, enables efficient and timely information exchange among agents, making sure to minimize unnecessary computational demands and data loss. In conclusion, the planner's topology is more than the structure. It's about creating a system where agents can interact and cooperate and execute plans effectively within the dynamics of the game world.
Now that we have established our planning architecture, let's explore the dynamics of the planning process itself. Ultimately, this process boils down to a search problem over the planning domain, with emphasis over the various aspects of the search approach, depending on goal representation. When goals are represented as world states, as with strip-like planners, the focus is on search direction, and we encounter the choice between forward and backward search. Forward search builds the plan from the initial state towards the goal state, with the advantage that we create the tasks in the order that they should be executed. However, it can become too exhaustive due to combinatorial problems, not even leading to the goal state. Thus, backward search is often preferred. It starts at the goal and works backwards. However, this approach can also become too exhaustive, as each task introduces new sub-goals that need to be searched. For this reason, pruning strategies become crucial here to manage the search space effectively and prevent it from growing excessively. In HTM planners, where goals are compound tasks, the emphasis shifts towards task decomposition order. Most HTM planners use total order decomposition, sequentially evaluating and executing tasks as planned, thus getting the benefits of both forward search, because you only evaluate actions relevant to the current state, and backward search, by only considering actions relevant to the goal state. Alternatively, although less common, partial order decomposition has been used, for example, for mission generation in games like Arma 2. It prioritizes the decomposition of more critical tasks first, aiming to identify potential plan failures earlier. For example, if a method decomposes into regroup and move as group, we might evaluate the harder preconditions of the move as group task first. So if we fail to find a solution, we can just save the time and cost of reevaluating, regroup, and just move on to finding another plan. In summary, we're looking for a search approach that allows our architecture to efficiently achieve its role while minimizing computational demands. All search strategies have their pros and cons, but optimization is key to making sure that they are more effective. Let's explore how to optimize search space, plan quality, and performance. An advantage of planners is that they inherently limit the search space through the use of preconditions, focusing only on actions that meet these specific criteria. Thus, a very long-hanging fruit is ensuring that preconditions are accurately defined. Additional constraints on actions or goals can further streamline the search space, making the planning process more efficient. For example, in Shadow of Mordor, planners narrow down the actions they can consider based on character roles. So for an investigator, you would only consider actions like investigate suspicious objects and ignore all others. Regarding plan quality, we can optimize by using heuristic, which is common in strip-like planners, or hierarchies, the standard for HTMs. Heuristics coupled to a strip's breadth-first approach likely leads to optimal plans, since it will select it from all viable plans. However, this also makes them extremely memory intensive because they require comparing multiple plans. Fear illustrates the effective use of heuristics, where action costs are calculated based on satisfied preconditions. Tomb Raider takes a more dynamic approach, adjusting the costs associated to an action based on its effectiveness throughout gameplay. In contrast, Hierarchy is optimized by considering partial plans rather than individual actions, in a manner closer to human reasoning, thus reducing memory usage. However, they are limited to predefined solutions, so the quality of the plans depends heavily on having a well-defined task network and the right decomposition order. Yet, depending on what we're using the planner for, trading off some quality to free up some memory is often worthwhile, which leads us into optimizing performance. In a dynamic game environment, swiftly finding and starting to execute a feasible plan often trumps calculating a costly, optimal plan that will likely fail regardless. The time slicing used in Transformers, for example, exemplifies how we might save some resources by accepting this fact. It involves distributing the planning process across multiple frames, allowing agents to start executing partial plans while the planning continues, thus distributing the computational burden to enhance online performance. To conclude, we are looking to achieve efficient search space and good plan quality without compromising on performance. This balance is crucial to adapt the planning process to the dynamic and interactive nature of video games. With the plan creation process mapped out, it's time to move on to part 9 and discuss how we should execute these plans. At its core, it can be boiled down to 3 easy steps. Step 1, try and execute the plan. Step 2, fail and entertain or annoy the player along the way. And step 3, try something else to continue entertaining or messing with the player. And that's the thing. It's important to keep in mind that, unlike academic settings, the true measure of success isn't merely achieving goals, but doing so in a way that elevates the player's experience, or even failing in a manner that adds to the game's appeal. So, in game settings, execution is more than just following a set plan. It's about dynamically responding to the game world, ensuring that the AI continuously contributes to an enriching gameplay experience. So, let's look at some of the scoping mechanisms. As we discussed, the stochastic, dynamic nature of games means that anything can happen between plan creation and execution that would lead to plan failure. A simple way to deal with this dynamism is to reintroduce some of the reactive behavior of behavior trees and state machines. For example, primitive tasks like go to could be introduced as micro behavior trees, so that when the agent is executing these tasks, it would take advantage of the quick reactive logic to jump over obstacles, duck, or look at some target. The second aspect to consider is reevaluating the plan and replanning. We can begin by considering to what extent should plans be reevaluated. In most cases, reevaluating the entire plan is too resource intensive. Therefore, most games reevaluate only the immediate next step to prevent imminent plan failures. However, the plan might still be doomed to fail 2 actions down the line, so if performance allows, reevaluating more than 1 step ahead might make sense. We must also consider when to reevaluate and when to replan accordingly. Since many tasks require information from, say, a ray tracing system, reevaluating periodically might be too costly. Thus, we might opt for an approach when we reevaluate based on certain events. For example, this approach was used in Dying Light, so that if the player got hit, the goal changed from attack to react with playing. Still, there are times when replanning periodically is simply necessary because of the structure of the planner. This is the case we mentioned earlier, where we have no world propagation in place during planning. In these cases, the world state might change too quickly from the initial state and lead to plan failures. This approach capitalizes on a very optimized planning process to brute force adaptability. We replan periodically and very quickly as a way to avoid plan failures. Killzone 2 used this approach, creating plans 5 times per second for every character. This had the added advantage that, because replanning is done often enough, reevaluation can become unnecessary. How we replan is also important. Unlike academic settings where partial replanning is common, in games, plans are usually shorter and the planning process is so optimized that simply creating a new plan from scratch is usually the way to go. Lastly, perhaps a unique aspect of replanning in games is the importance of having smooth transitions and natural-looking behavior when we're switching plans. In Killzone 2, for instance, when the plan became obsolete, backup branches in the HTN were switched to make the agent do something seemingly relevant while waiting for the new plan. With the planning and execution process mapped out, we can now consider what tools might make the whole developing process easier. The planner's domain is not static. It evolves with the game's development. New actions, effects, and preconditions emerge, urging for a tool that allows for easy adjustments. Thus, an editor tool, like the one offered by Unreal Engine, is invaluable here. It provides the agility to modify planner parameters and define actions efficiently, a necessity in complex and large-scale projects. When it comes to debugging, a simple runtime debugger might not be enough given the dynamic nature of games. This is exacerbated by the foresight that is inherent to planners, which makes deciphering their behavior by tracing back the search notoriously difficult. Thus, having a good tool to keep a history of the agent's goals, the statuses of their plans, and their executed actions is extremely useful, especially coupled to a method of recording and playing back the gameplay to reproduce situations and trace the planning that went on. And with this, we have reached the conclusion. We saw how classical planning systems like strips and HTNs have seen some commercial use in video games to facilitate complex agent behavior. However, they still had to be heavily modified to operate smoothly outside their academic niches. The inherently dynamic nature of video game provided a considerable challenge to combining the long-term formal planning with natural-looking, adaptive, flexible agent behavior. But, and this is more of a personal take, there's also an opportunity. With the boom of deep models, the sort of intelligence solved by classical AI seems to have gone a bit out of fashion. While deep reinforcement learning systems are promising, they still have not fully solved the sort of formal planning and reasoning that good old-fashioned AI look to implement. Perhaps going back a bit, we look for ways to reintroduce some of this formal planning, taking the strengths of modern systems to make the planning contingent with the execution and adapt it to real-time environments. This might bring some newfound appreciation to the sort of intelligence that classical systems sought to offer.